What's the name of the process that changes the envelope of an RF wave to carry information? That process is called amplitude modulation. And the key to this, the key to understanding this is the envelope is the shape of the outside of the wave. Here you have the carrier, and here it's being, the amplitude of the carrier, the power in it, the height of it, is being modified by the modulating waveform. And the envelope is the outside shape of it. Okay? The only way to modify that outside shape of it is by changing the power of it. Okay? And or changing the amplitude of the wave. And so if we modify the envelope, we are using amplitude modulation. What's the name of the process that changes the phase angle of an RF wave to convey information? Now, they've thrown a whole bunch of stuff in here, and let's do a little answer analysis here quickly. We know that, or we should by this time know that, the process of changing a wave to convey information is called modulation. Okay? So that should throw out all of the other answers here except phase modulation for you, because modulation is the process of changing something about a wave to convey information. So phase modulation is what we call it when we change the phase of the wave to do that. Now, what does that mean? Here we see frequency modulation, and here you can see a wave, a carrier wave of a particular frequency or a particular wavelength. Okay, and we apply, the blue here is a modulating wave being applied to it. In this case, a square wave, and when it's at this level, we change the frequency to this wave. Okay, and we can see that it's a much shorter wavelength. This is exaggerated. In actual FM, you wouldn't be able to see the difference. You'd have to measure it with some kind of a frequency meter or a discriminator. And then we go back to this level on the modulating wave. We go back to the original frequency and so on. Back to here, we change the frequency again. That's frequency modulation. Okay. Now, what do we mean by phase? The phase of a wave is not a change. It's a third characteristic of a wave. And really, it's a comparison between two waves. It's not a change in frequency. It's not a change in amplitude. It's a change in the position of the wave in time. This horizontal line represents time. Okay? And so the blue wave here is phase shifted just a little bit later than the red wave. It's essentially the same wave, but it's been phase shifted just a bit later. Let's see what happens in phase modulation. You can see here that the frequency is not changing when we apply the modulating signal to it. Okay? Frequency is not changing, but if you'll look down here, you can see that we have only a part of that wave before it comes back and then continues in its normal carrier thing, and then when it changes back, here we have only part of the wave, not the whole wave, before it goes back to being its normal self. So what we've done here is to change the phase of this. We have shifted the phase of the wave a little bit for our modulation, and then when we were through modulating, we shifted it back to where it was. Phase modulation. And again, if you keep in mind the modulation is the name of the process that changes a wave to convey information, then you won't have any trouble remembering that this is phase modulation for the answer on this one. What's the name of the process that changes the frequency of an RF wave to convey the information? You should already be ahead of me on this. We know that changing a wave to convey information is called modulation, and this time we're changing the frequency, so we have frequency modulation. And here we see the frequency modulation that we looked at before. What emission is produced by a reactance modulator connected to an RF power amplifier? Okay, bunch of words there. Maybe you never imagined they could be strung together in a sentence in the English language. Really aren't any good clues up in here. But let's take a look at a block diagram of what they're talking about and see if we can figure out what's going on here. Okay, here we have a transmitter. Here we have a reactance modulator applying modulation to an RF power amplifier. Now, we're going to get something here. The reactance modulator is going to change the reactance of something in the circuit here. And that's going to cause a shift in the radio frequency or in the phase or something like that. To create a true frequency shift, we would have to be doing it back here in the oscillator. This is where the carrier frequency is generated. And to do a frequency modulation, a true frequency modulation, we would have to be applying that reactance modulator back here in the oscillator. And you can see that I actually did some cutting and pasting here because you can see just the tip of the arrow where I stole that reactance modulator to move it over here to fit the question. Okay? What you'll get when you apply it to a power amplifier is phase modulation that we saw in the diagrams earlier, the phase modulation, because we can't change the frequency at this point. We can only change the phase when it's applied to an RF power amplifier. Now, in terms of what it sounds like coming out of a receiver, what kind of a receiver you use to receive it and so on makes no difference in the world. An FM receiver receives phase modulation just fine. And a lot of transmitters that are called FM transmitters are actually phase modulated transmitters. But in technical terms and for the test, what you're going to get when you use a reactance modulator on a power amplifier is phase modulation. What type of modulation varies the instantaneous power level of the RF signal? Okay, we talked about that. What the power is the amplitude, isn't it? The amount of power in a signal is the height of the wave or the amplitude. So we know that the modulation that varies the power level of the RF signal has to be amplitude modulation. And we see that here. An amplitude modulation gives us this envelope on the wave. Here they're using the, I guess they're using the blue here to show the modulating signal also, but it also describes the envelope of the wave. Here, the envelope of the wave would be straight across because there's no change in amplitude. Same thing here. The envelope of the wave would be straight across because there's no change in amplitude. But with the amplitude modulation, you do get the change in amplitude. What's one advantage of carrier suppression in a single sideband phone transmission? If we take a look at our single sideband, as we've done before, you'll remember that we generated two sidebands, and then we took out the carrier because we didn't need it. It contained no information. And we took off the sideband we didn't want because it had redundant information. You remember that the lower sideband on the lower frequency side of the carrier has exactly the same information as the upper sideband, which is on the higher frequency side of the carrier. And so if we transmit only that sideband, we make much better use of the available transmitter power. And that power can be used more effectively. All of the power now is being used to transmit information. Okay? If we transmit this, we're using transmitter power to transmit a carrier, which contains no information, and another sideband, which contains the same information as this one. So one advantage is that the transmitter power can be used more effectively. Which of the following phone emissions uses the narrowest frequency bandwidth? Think about that picture we just saw. Think about double sideband, single sideband, and you'll remember that we have cut the bandwidth of the signal in half by using the single sideband. Which of the following is an effect of over-modulation? Let's see if any of these make sense. Would we have insufficient audio if we over-modulated? No. We'd probably have too much, wouldn't we? Would we have insufficient bandwidth? No. We'd probably have too much. Would we have frequency drift? Probably not. Modulation shouldn't affect frequency. But we would have excessive bandwidth as a result of overmodulation. What control is typically adjusted for proper ALC setting in an amateur single sideband transceiver? If you look on an amateur single sideband transceiver, you'll see a meter, and it shows power, it shows SWR, it shows S units, and down here you'll typically see a needle scale down here that shows ALC. That's the automatic level control for the signal being fed into the modulator. And the control that you typically use to adjust that is the transmitter audio or the microphone gain. On most transceivers, it's probably called the microphone gain control. And your manual, your operator's manual, will tell you how to set that to keep the needle within the proper range on the ALC when you're transmitting. What is meant by flat topping of a single sideband phone transmission? The signal distortion is caused by excessive drive. Here's what your signal should look like in a single sideband test signal. Okay, it should look like this. It should have this nice smooth curve here at the top. And if you overdrive, then you'll drive some of the amplifier circuits to cut off to where they can't amplify anymore, and you'll get this kind of an effect. What happens to the RF carrier signal when a modulating audio signal is applied to an FM transmitter? The carrier frequency changes proportionally to the instantaneous amplitude of the modulating signal. Okay, now a couple of clues here in analyzing the answers. What happens to the carrier when a modulating signal is applied to an FM transmitter? Okay, the amplitude is not going to change. The phase is not going to change. So you can eliminate those two answers, which leaves you only with these. One of them says the carrier frequency changes proportionally to the instantaneous amplitude of the modulating signal. This one says it changes proportionally to the amplitude and the frequency. Correct answer is it changes proportionally to the amplitude of the modulating signal. What signals would be found at the output of a properly adjusted balanced modulator? A balanced modulator is a circuit that combines signals, and it does it in this manner. If we have an input here of a carrier, an RF oscillator and a carrier here, and we put in a speech amplifier here, we're going to get two signals, two products out of that balanced modulator. We're going to have the sum of the two frequencies, and we're going to have the difference between the two frequencies. Okay, and in this case, where we are using the balanced modulator in a single sideband transmitter, what we're going to have are both the upper and the lower sidebands. We're going to have the carrier plus the audio frequency, and we're going to have the carrier minus the audio frequency, or the upper sideband and the lower sideband. So we're going to have a double sideband output signal. Now, the beauty of the balanced modulator is that it eliminates the oscillator signal, the carrier signal, that in an ordinary mixer would be coming on through. It cancels out. The RF oscillator frequency cancels out in the balanced modulator, so you get only the upper sideband, lower sideband signals. And that's how we generate double sideband, which we then filter off one sideband to make the single sideband.